Hello students, welcome back. The second half of chapter 7 is about trigonometric equations, but you're going to feel as if this is a continuation of earlier trigonometric equations we did before chapter 7. Well, that was by design, in order to avoid a situation that you have to cram up too much information in such a short period of time and consequently overload yourself. I divided the trigonometric equations part into two and then did some trig equations early on, just with some trigonometric functions and Pythagorean identities. Now we have more identities here, especially double angle identities, and consequently the trigonometric equations here will be a little bit more complicated. But with some prior exposure, you'll feel much better this time. Okay, let's begin. We begin with graphs of trigonometric functions, and here is the graph of sine function going up and down, starting from 0, 0, and this is an odd function. Sine of negative theta is negative sine of theta. Another feature is that this function is symmetric with respect to x equal to pi over 2 or 3 pi over 2, or any odd pi over 2 to tell the truth when we have this top of the mountain or floor of the valley. Now this is a graph of cosine function, and similar, we have going up and down, but the top of the mountain is actually on the y-axis here, so the symmetry is with respect to the y-axis, or x equal to 0, so this is an even function. But not only 0, the symmetry takes place for x is equal to any multiple of pi. Now here is a graph of the tangent function along with the graphs of sine and cosine together. Red is sine, green is cosine, and blue is tangent. Please note that the tangent function hits the vertical asymptote when the denominator hits 0. The denominator is a green function, the cosine. Also, the blue function, the tangent function, hits 0 when the numerator hits 0, and the numerator is a red curve, that's sine function. Okay, now let's review inverse trigonometric functions, arcsine, arccosine, and arctangent respectively. If we restrict our domain of sine function to negative pi over 2 to positive pi over 2, then that portion passes the horizontal line test and it is 1-to-1. So we can consider its inverse function or arcsine function. And because inverse functions basically takes y to x and x to y, so domain becomes range, range becomes domain, and the symmetry with respect to y equals to x, because y-axis is mapped onto x-axis, x-axis goes to y-axis, vice versa. And here is the graph of cosine function and arccosine function together in the same viewing window. And we have graph of cosine function going up and down, but if you restrict the domain from 0 to pi, not all the way to 2 pi, but 0 to pi, then we have a 1-to-1 function, the dark region here, and consequently we have inverse function, arccosine, the red graph here. And the same behavior takes place. Inverse functions take x to y, y back to x. Consequently, there is a symmetry between x-axis and y-axis. That's visible by the symmetry with respect to the principal diagonal. Now here is a graph of the tangent function and also arctangent function, by the way. And tangent function goes from negative pi over 2 to pi over 2. And in that region, we have a 1-to-1 function. And consequently, we have a inverse function, arctangent function, and the vertical asymptote becomes horizontal asymptotes. Domain becomes range, range becomes domain, the same deal. And how do these inverse sine, cosine, and tangent functions help? Well, here is the summary. if you have y equals sine of x, then you'll have one solution from arc sine, but also there's an extra solution. Pi minus that is also a solution. Consequently, we have those two solutions, blue and red, in the standard domain 0 to 2 pi, or negative pi to positive pi. And then you can add any multiple of 2 pi so that those pair will be repeated in the next domain, and the next domain, and the next domain, and so on and so forth. Here's a visualization, as a matter of fact. Not too good. Okay, that looks a little bit better. I mean, the program is randomized, but what I want is to have some separation between these 2 points and also away from the x-axis for better viewing. The blue point here represents the blue solution given by arc sine. And the other solution is pi minus of that, and that's coming from the symmetry of the graph of the sine function with respect to the vertical line x equals pi over 2. And if you have a pair of solutions in the standard domain 0 to 2 pi or negative pi to positive pi, depending upon what kind of viewpoint you have, the pair of solutions will be repeated in the next interval, and then in the next interval, and then the next interval, and so on. And that next part will be taken care of by adding any 2k pi. If you have to restrict your domain, then you'll have to select appropriate k value for that. Now here's a visualization for cosine function, cosine equation. At y equals to cosine of x, then you have one solution from arc cosine. X equals to arc cosine of y. That's the blue solution here. And negative of that is automatically a solution because cosine is an even function. So plus or minus of that, and then that pair is going to repeat it, and then repeat it, and then repeat it as you add 2 pi, 2 pi, 2 pi, or in the left hand side as well by subtracting 2 pi. Now if you have tangent function, that's a little bit different because period of tangent is just pi, not 2 pi. So you don't really need a pair. You just need one solution from arctangent and then add arbitrary k pi. Not 2k pi, just k pi. And how do we use these to solve some trigonometric equations? Let's begin a linear trigonometric equation. For example, how about this kind of problem? Solving sine of x from the equation, you just flip 1 to the other side, and you get 3 of x is equal to 1, and divide by 3, you get sine of x is 1/3. And what do you get? You get one solution, arc sine of 1/3, blue solution, and then red solution. Maybe it's a good idea to color code them, red and blue. So arc sine gives one solution, and then pi minus of that gives another solution. And then those pair of solutions will be repeated in the next period, as you can see here, and then the next period, and then the next period, also to the left hand side. How about for cosine? Well, solution is pretty much straightforward. Move 5 away and then divide 4, and then, oh wait a minute, cosine of x is negative 3/4, not x is negative 3/4, excuse me. Consequently, x is arc cosine of negative 3/4, but let's see, because cosine is an even function, you can actually drop out this negative because arc cosine of 3/4 and arc cosine of negative 3/4, actually what am I talking about? That doesn't drop out, excuse me, sorry about that. Arc cosine of negative 3/4, okay, that stays there. It's just that even function generates plus and minuses. Plus will be the blue point, and then red will be the minus of that. Sorry, even function, yes, but this different place. This plus and minus, that's coming from even function. And here's a visualization. And those pair of points, those solid pair of points, will be reproduced in the next period and the next period as you add any multiple of 2 pi. When k is negative, then you go to the left hand side. And tangent problem, okay, let's look at the tangent problem, and let's not spend too much time. So divide both of them by cosine from the original equation. Then we have sine over cosine. So tangent is -3/2, so you can find out the solution by taking arctangent. Once you get arctangent, all you need is just plus k pi. Okay, those were linear trigonometric equations. And how about quadratic or higher? Well, some quadratic trigonometric equations are straightforward, but that's rarely the case. You'll have to simplify that, or as a matter of fact, it's not really a simplification. You'll have to make it well posed by appropriate trigonometric identity most of the time. The first example is one of the rare cases that you can go straight ahead and factor it and solve. If you do, this is what you're going to get. 6 sine of x, sine squared of x, minus 5 sine of x minus 4 equal to 0. You can factor as 2 sine of x plus 1 times 3 sine of x minus 4 equal to 0. I'm not going to spend class time on how to factor. That should have been done in elementary algebra and reinforced in intermediate algebra. And then by the time you take college algebra, you should have mastered. Here in pre-calc, you are expected to know. Everybody is expected to know. And then once you factor and set each factor equal to 0, you get one solution from the first factor. Sine of x is -1/2. And the other one, sine of x is equal to 4/3, is an extraneous solution because sine can never exceed 1. Okay, sine of x is -1/2, and you can find out through taking arctangent, but another way to do that is to look up the trigonometric diagram, because sine of x equals -1/2. -1/2 is coming from one of those basic angles. This is what I'm talking about. Here, find out the second coordinate equal to -1/2. You get 11 pi over 6 and also 7 pi over 6. 11 pi over 6, as a matter of fact, is equivalent to -pi over 6. But if you use 11 pi over 6, that's perfectly fine. And you can add 2k pi, so you're going to cover everything anyway. From 4/3, of course, you don't get anything. Let's see, do we have justification? Well, here we go. We have two solutions here, green solution and red solution. Red solution in the left-hand side of the y-axis is actually -pi over 6. And then this hollow red one, the third solution, one in the right-hand side of this green dot, is actually 11 pi over 6. And depending upon what kind of domain you're looking at, from 0 to 2 pi or -pi to +pi, you'll have to select appropriate value for that, or you can adjust your k value to another integer. And that's not too difficult, so I'm going to leave those to students. And that was one of those rare cases that you can factor straight ahead. Well, the second problem with cosine, you can do pretty much the same thing. But what if you have sine squared and cosine squared mixed up like this? Or you have cosine squared but not plus cosine of something, but say -2 sine of x or something. What if you have both sine and cosine together? In that case, you can use the Pythagorean identity, because cosine squared plus sine squared is equal to 1. So cosine squared and sine squared are essentially interchangeable. For example, in problem C, this cosine of x must stay the same. This linear term must stay the same because it has first power, so Pythagorean identity does not apply. Consequently, this is okay, cosine squared. The sine squared is not okay, so you'll have to apply the Pythagorean identity to change it. And this is how you do. Change the sine squared of x into 1 minus cosine squared. That's because this cosine of x, this red highlighted function, dictates the direction. And consequently, what we get? We get a quadratic equation of a cosine. After some algebraic manipulation, you can factor it, and consequently, we get cosine of x is 1/2, and cosine of x equal to -1. And taking arc cosine of plus and minus arc cosine of 1/5 and looking at the wheel, you can get this kind of answer.